Hello everyone, in this video we are going to be going over calorimetry, kind of just like a basic review. Um, this is like another one of those topics that is kind of difficult to really understand and grasp the concept of it. The algebra and the math is fairly easy. There's not really much to worry about here. Um, Again, pretty easy. Um, but if you are having trouble with kind of just conceptualizing the things, I would suggest watching another video. I personally love watching YouTube videos to help me study. That's like why I made these videos, because I know it helps me. Um, but yeah, definitely reach out to some other YouTube videos if you are struggling with this one, because this one is kind of difficult to understand conceptually, but you don't really need to understand it conceptually, honestly, to do the math. But for some people, like that's how they like to do math. They like to understand how it works. But yeah, so anyways, let's get on into this video. So again, we are going over calorimetry, right? So basically the only equation that you have to know for calorimetry is Q is equal to mCAT. People say mCAT, but it's Q is equal to mass times specific heat and the change in temperature. I always remember it, like, I know we don't have to memorize equations, but I always just do Q equals MCAT because it looks like a CAT, but it's a delta T. So Q equals MC delta T, right? So now let's look at exactly what all these mean. So Q is the heat in a reaction, which is measured in joules. M is the mass of whatever it is, whether it's an aqueous solution, whether it's a metal, whatever, that's the mass. The specific heat is C, which is measured in joules per gram times kilogram, or times Kelvin. Oftentimes you also see that times Celsius. They're the same conversion, so you don't necessarily have to worry about that. If you feel more comfortable changing it from Kelvin to Celsius, go for it. I'm pretty sure the conversion, like to go from Celsius to Kelvin is like, you have to add, I think it's like 273. I'm gonna check that before I like K2C formula. Yeah, so 273.15 is what you do there in order to get that. Okay, moving on, we have the delta T, which is change in temperature. Oftentimes we put this in Kelvin. Again, you can put it in Celsius when you're dealing with a change in it because it doesn't matter, right? So if we look at something like 20 degrees to 30 degrees in Celsius, and then we'll do that in Kelvin, which will be about 293 Kelvin to 303. Let me just do the math to make sure I did that right. Yeah, 303 degrees Kelvin, right? So if we're doing the change in temperature for both of these, which is final minus initial, we have 30 minus 20, which is equal to 10 degrees Celsius. And then here we have 303 minus 293, which again is going to be 10 degrees Celsius for delta T. So that's just showing you that the conversion, like, it doesn't matter if you're doing temperature final minus temperature initial, they're going to be the exact same thing because, you know, there's no weird conversions in there, right? Okay. So now going on to talk about what specific heat is, just kind of as like a conceptual thing. You don't have to really understand this, but it does help a little bit when you're doing the calculations to kind of see like, oh, am I doing this right? So what specific heat does is that tells us the amount of heat required to change the temperature of a substance. So let's just think about that for a second, right? Professor Sherlock likes to use the example of glass and metal, which I think is always really good, right? So you guys have probably experienced this before where you have a metal and you're heating it up with something, whether you're roasting a marshmallow or you're using a metal spoon to mix your pasta because you couldn't find a plastic one or something, right? So you use that and it starts to burn your hand because that heat travels up it really quickly and quickly reaches your hand. So the metal is able to heat up really fast. So I have an example here of iron. Iron has a very low specific heat, so it takes a lot less energy and heat in order to bring up the temperature. But then when we think of something like wood, let me even just look up the specific heat of wood. Specific heat of wood. I don't know if this would actually come up. Okay, so specific heat of wood. 1.67 is what they have calculated here in joules per gram degree Celsius. So it's a lot more than 0.45. So when you have a wooden spoon, it's not going to burn you as easily because that heat, it requires a lot more energy and heat for it to travel up and change the temperature. I also have water here. Water is one of the most insulated thing ever. Like, that's why they use it in a lot of heaters and things. It's because it holds the heat very well. So it's really hard for water to lose heat, and it's really hard for it to gain heat. But that's just kind of like another example there of like showing you the difference between the two of something that's really high and something that's decently low. But yeah, it's always good to think about the metal, right? Metal has a low specific heat. It's going to burn your hand much faster than something that is not a metal, like wood, right? So that's why we have wooden spoons to mix our pasta. So I'm going to go into doing practice now because, again, like, this is a fairly easy topic. The math is pretty easy with this, so we're going to get into some practice. The specific heat of lead is 0.13 joules per gram degrees Kelvin. Well, Kelvin, you don't even need the degrees there. How much heat is required to raise the temperature of 15 grams? I'm going to like underline the things that are important. 15 grams of lead from 22 degrees Celsius to 37 degrees Celsius. All right, so let's look back at our equation. So we have Q equals MCAT. So let's see what we can plug in. So the specific heat we can plug in. So I'm going to write Q is equal to, first thing actually is mass. So let's see if we have that first. So we do have mass. So I'm going to write that down first, actually, 15 grams. And we are looking for the heat. So I'm going to leave Q by itself. I'm not going to do anything to Q. So Q is equal to 15 grams. And then we have the specific heat at 13 joules Kelvin. 0.13, and then to do the change in temperature, I'm going to do the temperature final minus temperature initial. So the change in temperature is always going to be equal to the temperature final minus the temperature initial, right? Yeah, so it can be negative technically. I think in most of these problems we're going to be dealing with a positive change in temperature. But yeah, so just as a reference, so change temperature is always going to be final minus initial. So let's do that right now. So we're raising the temperature from 22 degrees Celsius to 37 degrees Celsius. So we're going to go 37 degrees Celsius minus 22 degrees Celsius. All right, so I'm going to rewrite this and write out the 37 minus 22, 37 minus 22, I got 15. And now we're going to multiply all those things together. So 15 times 15 times 0.13. And I got a Q value of 29.25, but we can only do 2 sig figs, so I'm just going to keep it at 29, and that would be joules. And I'm just going to check my answer really quickly and see what we got in class, because we did do this one in class, and we got 29 joules. Cool. Alrighty, so let's move on to the next problem. This one is a little bit tougher, but as always, you guys can challenge yourselves, pause the video, try this yourself, but if not, I'm going to be going over it right now. Okay, so in a reaction, a liquid with a specific heat of 0.13 joules per grams Celsius weighs 15 grams, and it releases 29 joules of heat when it's reacted at 22 degrees Celsius. Find the final temperature in degrees Celsius. All right, so here we're going to find the final temperature. So I know that that's going to be the thing that we're looking for. So again, let's write out our equation. Q equals mCAT. And then we will look and see what we have, right? So Q first. Do we have Q? All right, let's look. So that's the heat, specific heat, that's the mass, releases. All right, 29 joules, right? So that's going to be our Q, 29 joules. Cool. So next thing is mass. We have mass, that's 15 grams. And the specific heat, I just saw that, that's up here at 0.13 joules. And just to keep in mind that the specific heat for everything is going to be different. It just so happened that the two problems that I picked had the same specific heat. But as I was saying in the last few slides, that the specific heat for water is much different from the specific heat of lead, which is much different from the specific heat of iron, which is much different from the specific heat of wood. So every single material has a different specific heat. So just keep that in mind. They're not all going to be the same. Okay, the next thing we're going to look at is the change in temperature. So we're going to do, again, temperature final minus temperature initial. So I'm going to rewrite this with the value that we have. All right, so temperature final minus temperature initial. So we're looking for the final temperature. So we're going to make that stay the same. We're not going to add a number to it. And it's heat when reacted at 22 degrees. So that's what we're starting at. So this is our temperature initial, because this is what the temperature of the reaction is first occurring at. So we're going to write minus 22 degrees Celsius. And then we are going to do some algebra here, and we're going to multiply these two together. So I'm going to do that really quickly. 15 times 0.13, we get 1.95. Temperature final minus 22 degrees Celsius. And again, we're just going to do some simple algebra here, and we're going to distribute this. So we're going to do 1.95 times this, the temperature final, and then 1.95 times negative 22 degrees Celsius. So we will get 1.95 temperature final minus 0.95 times 22, which will get us 42.9. And then we're going to add this to both sides in order to get rid of it. 42.9. Let me fix that because that's going to bother some people. I know it will. 42.9 plus 29. So here we will get 71.9 is equal to 1.95 temperature final. And then we're going to divide these both by 1.95. I'm going to keep writing it over here. After we divide that, we get that the temperature final is 36. Let me see how many sig figs I can get. All right, I can get 2 sig figs, so we're going to write 37 degrees. They want it in degrees Celsius, so I'm going to write it in degrees Celsius. And that would be our answer. Let me just check that one, and also got the same answer from in class. All right, so that is calorimetry. As I said before, definitely watch some videos if you feel like you're kind of struggling to understand this one. Again, it can be really tough to kind of conceptualize it and everything. But again, like the math in it is fairly simple. As long as you get everything in the right place, you should be good to go. Just do some basic algebra and you'll be good. Same thing as always. Thank you all for watching, and reach out with any questions. Thank you.